Hello, this is Professor Bennett one last time from digitalaudiotheory.com. This programming example, the final one, comes from Chapter 14, which covers digital modeling of analog audio systems, including the impulse invariance method, the bilinear transform, as well as frequency sampling. In these programming examples, 14.4.2 and 14.4.4, we'll apply the frequency sampling method to convert an RLC analog filter into a digital filter. Now, frequency sampling is the method of capturing the magnitude of the desired frequency response and constructing a digital filter by assuming either linear phase or minimum phase. So this should tell you that this is going to be an FIR filter. The IR from this digital filter is then obtained by performing the IDFT, resulting in an FIR filter set of coefficients. Now, care must be taken since frequency sampling can result in time aliasing, in which the IR tail actually wraps around to the beginning of the IR. But this artifact can be minimized by using a sufficiently large number of frequency samples in, which will be equivalent to the resulting filter order. So let's start with linear phase. A linear phase filter will have no phase distortion, but a relatively larger group delay. The linear phase is constructed by determining the group delay, simply the filter order divided by 2, that then becomes the slope of the phase, which is of course linear and intersects at the origin such that the phase is 0 radians at frequency bin k equals 0. The slope of the phase is n over 2, well, minus n over 2, so at the frequency bin corresponding with the Nyquist frequency must have a phase of minus n over 4. With the phase response can be simply written as negative k over 2 for k equals 0 to n over 2. So note that we're going to only construct actually half the phase response from 0 Hertz bin up to Nyquist. But recall that the spectrum is symmetrical about Nyquist, so we're going to take advantage of that property. So let's first set up our digital parameters. We're going to do a 44.1 K system with 1024 points. That should be sufficient to avoid any sort of time aliasing. Next, let's define our analog prototype. So this is going to be an RLC filter with a resistance of 10 ohms, an inductor with an inductance of 2 millihenries, a capacitor with a capacitance of 5 microfarads. So this is going to have a center frequency of 1.6 kilohertz with a bandwidth of 0.8 kilohertz. So we're going to construct our frequency vector here from 0 in steps of fs over n all the way up to fs. So f should have 0 up to fs. Okay, so this is a textbook lookup type of thing. The digital audio theory does not cover any sort of analog or Laplace theory. So if we look it up, though, we can find, even just on Wikipedia, the transfer function for a continuous RLC. And it's governed by this transfer function right here, where these are the numerator coefficients, and these are the denominator coefficients. So we're going to analyze this analog transfer function at these different frequency locations inside f. Remember, these are equally spaced by fs over n. And instead of using freq z, we're going to use freq s here. This is for S domain, which is analog. Okay, so here we have our HC, C for continuous, transfer function. Now we're going to construct the digital model. The linear phases we'll construct first. Okay, so the slope is negative n over 2, and then right at Fn, which is at n over 2 plus 1, our Nyquist, the phase is going to be exactly minus n over 4, as I previously mentioned. So let's evaluate that. Then the baseband transfer function, given by HBB, is constructed by combining the magnitude response, given by our continuous transfer function, times e to the j2 pi of our times our phase response, which is the linear phase that we just constructed. So we're going to take this linear phase and we're going to combine it with our magnitude that we get from sampling the frequency response of the analog system, the RLC. Now remember, this is only in the baseband. This is only half of our digital model. So next, the conjugate portion on the lower half of the complex plane must be constructed. This is done by taking the conjugate of all the bins between 0 Hz and Nyquist. The complete digital model is generated by mirroring the conjugate portion about the Nyquist frequency. So here's conjugates of everything, excluding Nyquist and DC. Remember, Nyquist is the mirror point, and DC does not show up again until we get into our next image. So we're going to take all those conjugate parts, we'll flip them, and they're going to be mirrored about our baseband. And that's going to give us our complete model, HM. So the IR is then the IDFT, the inverse discrete Fourier transform of that frequency response that we just constructed. Come on. There we go. So let's double check this IR. We're going to take the IR, we're going to compute its digital frequency response with freq Z, and we're going to compare its magnitude to the original analog prototype. So here's our frequency response of this impulse response that we're going to use as our coefficients for our FIR filter. Now let's first plot the analog prototype. There it is, continuous. Let's also plot the digital model on top. Look at that. We can verify that these do indeed match. Looking great. And let's take a look at the IR for this. There you have it. A symmetric linear phase FIR filter. All right. Now, we may want to repeat the same example, but instead with minimum phase. How do we construct the minimum phase? The lowest group delay can be achieved with the minimum phase filter, which is why we might want to use it. Interestingly, the minimum phase filter, let me say that again, the phase of a minimum phase filter can be derived from its magnitude response. This remarkable property is defined according to, now get ready for this, the negative imaginary part of the Hilbert transform of the log of the magnitude response. Seriously. Now, you may not know what the Hilbert transform is. It's simply a phase shift of a signal by 90 degrees. So, we're going to construct a minimum phase IR using the same analog prototype as before, except this time we have to define the frequency range over minus fs over 2 to plus fs over 2, since MATLAB's Hilbert function, which is what we need to use for the Hilbert transform, requires that the 0 Hertz component be in the middle, as opposed to how we did it before, where it was on the left-hand edge when we went from 0 to fs. Okay, a slight difference. So next we construct the phase using the Hilbert transform, using this gnarly equation. So let's make sure all of our stuff, here's our analog prototype, same as before. We're going to generate a frequency vector that goes from negative fs over 2 to fs over 2, but the same n number of points to analyze it. Our analog or continuous transfer function is exactly the same as before. No difference there. Okay, here's that gnarly equation. Our minimum phase is the negative imaginary part of the Hilbert transform of the log of the magnitude of a frequency response. Okay, so let's evaluate that. So by default, MATLAB phase jumps greater than pi are wrapped, they call wrapped down to negative pi. So we're going to use this unwrap function to undo that wrapping. So this will keep the phase continuous with no big jumps. So finally, we need to construct the digital model from the magnitude of the analog prototype and this minimum phase that we just constructed. Here we go. The spectrum will be shifted for the IFFT, which actually wants to see 0 Hertz in the first element and FS in the last element. So we're just going to restructure this model a little bit by moving, the conjugate part. Instead of from the beginning, we're going to move it to the end. That's just how IFFT wants to see it. So we're going to grab the impulse response. And again, after taking the IFFT to extract the IR, we're going to load up the original analog prototype, and we're going to take the frequency response of this IR, and we're going to compare them. So let's open up a new figure here. All right, we've got the frequency response of the IR. So here is the original analog prototype. And again, the digital model. Look at that. A perfect fit. A slight deviation. Very, very close. Let's take a look at the impulse response. There we go. All the energy is compacted right towards the beginning. So we can compare the minimum phase IR to the linear phase IR. Note that the peak is at the beginning instead of in the middle, as we saw with the linear variant. So that's it for this entire video series from my text, Digital Audio Theory. I truly hope you enjoyed it and learned something from these videos. This is my favorite topic in the world, digital audio. So long for now, and thanks for watching.